Hi students, good morning to all. So in yesterday's class we have discussed regarding the displacement, velocity and acceleration of a particle in simple harmonic motion. So for that we have improved the equations also. So now in this class we are going to discuss regarding the concept of the force law in simple harmonic motion. So force law in simple harmonic motion. So before going to discuss about this force law in simple harmonic motion, which we should have to know regarding the one, so which is nothing much a restoring force. So force means, you know, so whenever we have applied some external force, the object can change its position. But here they are asking restoring force. For this restoring force, how we can determine this? So I have been given examples for simple harmonic motion. So one is the oscillation of a ball. So and then one more example is mass suspended by a spring. In these two examples, we have been observed here this position which we call it as mean position. Whenever we have been applied some force, the object which tries to change its position and then it will reaches to extreme position. So that bob it cannot stay for a long time. So what it will happen means, so one kind of force will act, that force which is nothing but restoring force. So restoring force is one, the particle which tries to come towards the mean position. So this is the mean position. And then this one we should call it as the extreme position. So this bob or particle which tries to come towards the mean position. How it is possible is because of restoring force. So regarding this restoring force which we have been discussing the concept of mechanical properties of solids. Whenever we have been taking a rubber ball and then if you press, that is the applied force. Whenever we have been removed that the ball which tries to come to its original shape and size, that force is nothing but restoring force. In the same way, here this restoring force is one. Whenever the particle tries to come towards a mean position, so that we should call it as a restoring force. So now we discuss the force law in simple harmonic motion. So regarding that, whenever a particle is in simple harmonic motion, that particle which tries to come towards a mean position, it cannot stay for a long time for extreme position. So it tries to come towards a mean position and then again it tries to move towards the other side. So that coming force, how it will be means that restoring force is directly proportional to its displacement. So that displacement which is denoted by x. Here we are not applying force. This is a restoring force. This restoring force which will be taken as a minus. So here this negative sign which it will indicate that the restoring force is always opposite to the direction of the displacement. So with the help of this, to remove this directly proportional, so which will be taken as, so F is equals to minus kx. So this is a force law in simple harmonic motion, where k is a force constant. So in the same way, we can take for this also. this what will happen, it will tries to move in downward direction or in upward direction. So this is a mean position. So this is a extreme position. So this bob which tries to come towards a mean position. So because of its restorative force. With the help of this, restorative force is always directly proportional to the displacement but in opposite direction. So with the help of this, we should give F is equals to minus kx. So with the help of this force law, now which we are going to find, so one important term which we can take as omega. So omega is nothing but angular frequency. So with the help of this, from Newton's second law, so what we know from Newton's second law, so which is nothing but, so F is equals to m, but here what we know, F is equals to minus kx. So with the help of this, which I can make it as, so F is equals to minus kx from force line simple harmonic motion. Here LHS equals to, so LHS are equal, we can equate the RHS. So with the help of this, which I can get here as, so minus kx is equals to m, where here A represents, A is equals to, so acceleration of the particle. So not amplitude, small a represents acceleration of the particle. But what we have to do, A is equals to, we have to do minus omega square x in previous class. So acceleration of the particle, we have to do A is equals to minus omega square x. If you substitute in our equation, so we can get here as, so minus kx is equals to, so m into A is equals to minus omega square into x. So minus gets cancelled, x gets cancelled. With the help of this, the force constant which we get here as, which is nothing but m into omega square. K is equals to m into omega square, which we can make. So in this way, which we can express regarding the force line simple harmonic motion. And then this, the force constant, which is very important for us, which we are going to use for further calculation purpose, where K, which I can call it as a force constant. K in terms of mass and angular frequency, we can take it as K is equals to m omega square. Okay, so next topic is oscillations due to a loaded spring. So this question which they may ask for 5 marks like this. So derive the expression for the time period of oscillation of a loaded spring using force law. So derive the expression for time period. This time period, so which is denoted by capital T, of a loaded spring. So using force law. So loaded spring means, so which you can take the example, so which you can take here as like this. So this is the one which you can call it as a rigid support. With the help of this rigid support, which you can suspend. For example, our flow. For this, which you can hang a spring. For this spring, which you have load some mass. Which has been suspended. So with the help of this, for this mass which is m, here we are ignoring the mass of the spring. Mass of the spring we are not going to consider in this case. So for this, whenever it has been oscillates, whenever it is oscillating, so that it will take some time. So that how much of time as it will be take to complete one oscillation. That time period on what factors it will be depend. So based on this, which we are going to consider. Here, let us consider a loaded spring which has been suspended from one rigid support, and on the other end which we have been suspended by some mass m. So with the help of this, which we are going to, so using force law. So that force law, so we know the force law, which is nothing but, so F is equals to minus kx. So with the help of this, which I can, so where k is a spring constant, or we can call this as force constant or force constant also, which we can. So from Newton's second law, Newton's second law, so which you can do here as, which is nothing but, which you know very well, so F is equals to M. Again I am using the previous concept, but this question will ask for 5 marks. So with the help of this, A is equals to minus omega square x. So this is nothing but acceleration of a what? So by substituting that in our equations, which I can get here as m into minus omega square x, that which is equals to minus kx. So with the help of this, minus gets cancelled, x gets cancelled. With the help of this, m omega square is equals to k. So in last class, in previous topic also have been put up to here. But now they asked, so we should have to prove the time period. For that, which I can write here as, so omega square is equals to k by m. But here what omega represents? Omega is nothing but angular frequency. But what we know, so that omega is equals to 2 pi by t, where t is a time period. But this equation is in terms of omega square. With the help of this, I can write here as omega is equals to root of k by m. But omega equals to 2 pi by t. By substituting that, so 2 pi by t is equals to root of k by m. They asked to find the time period, so I can send t towards this side and then root k by towards the downside. With the help of this time period t is nothing but, which you can get here as 2 pi root of k m by k. It will be reversed because it will come 2 pi by root of k by m. So time period of oscillation of a loaded spring, which is nothing but, it will depends upon the two factors. One is mass of the loaded spring and k represents force constant. Or here I have it taken as a spring, I can take it as a spring constant. So with the help of this, which I can do the time period. So this question which I can ask for 5 marks or 3 marks. So with the help of this, which you can do it as frequency. So frequency, which is denoted by f, but f is equals to 1 by t, because frequency is the reciprocal of its time period, which we have learned already. So with the help of this, which you can do that, which is nothing but, so 1 by 2 pi root of k by m. So in this way, which you can find the frequency. So this is regarding the oscillation due to a loaded spring. Okay, students, this is a question which they may ask for one more question. So this question already I have explained. So what is meant by restorative force? So the force which tends to bring the oscillating body from its displacement position to the mean position is called restorative force. So this one already which I have been explained here. I have been taken a bar, this bar which tries to come towards a mean position, from its displacement position. So whenever it has been moved toward this, it tries to come towards the mean position. So that force which we will call it as a restorative force. So then next question, what will be the change in time period of a loaded spring when taken to the moon? So on earth we have been done the loaded spring. That loaded spring, so which I have been taken here as like this. So it will be having some mass m. So then it has been taken to the moon. If you go to the moon, so what it will be happening is g value will be varies. So that g value will decreases. So but what about its time period? So we have to derive time period t is equals to 2 pi root of m by k, where m represents mass of the suspended body and k represents spring constant or force constant. So this time period, it does not depend upon the small g. So that's why we can write t is independent of g. It will not affected when loaded spring is taken to the moon. So which we can take to the moon also. The time period will be the same as well as on the earth, on the moon also. Next, how does the time period of oscillation of a loaded spring vary with spring constant? So we have been derived time period t is equals to 2 pi root of m by k. So if mass remains constant m, so then time period is inversely proportional to root of its spring constant. So we can remember this is simple equation. With the help of this, which we write here as a time period is inversely 1 by inversely proportional to the square root of the spring constant. So this is the topic. So in this class, which we have been discussed regarding the force law. So with the help of this force law, which we have been derived the oscillation of a loaded spring, that time period and then frequency which we have been derived. Thank you.